All right. Hello, everyone, and welcome to Handmade here, the show where we code a complete game live on stream. We decided on taking a absolutely ludicrous path to lighting yesterday because I guess just because I was feeling saucy. And so, yeah. We are going to go on a ridiculous ride. And probably it won't work because most of the time when you try to do something with rendering that's kind of weird and experimental, it doesn't work. But that's just the way it goes. And like I said yesterday, we already kind of had a success with the depth peeling. I thought that worked out really great, actually. And I'm super happy with it. So why not press our luck? Why not roll the dice twice? Yeah, probably it's not going to come up with, double sixes every time, but, You can't win them all, but you're certainly not going to win if you never roll. So let's go ahead and get started because there's nothing to talk about. We talked about it yesterday. It's the die has been cast, so to speak, I suppose. We just don't know what it's going to be coming up as. So today's day 394. You're going to want to start on day 393 for the source code if you're following along with the code at home. So let's go ahead and open up the project here. Oops, that's not how you spell handmade. That's how you spell handmade. And I'm going to go ahead and just run it here so you can see where we're at. And we'll talk about what our first steps are going to be. So right now we have a simple directional light source attached to the main character here that I can move around, right? So ignore the fact that the main character is moving around. We just care about the little light source that's moving around, right? And so what we're going to try to do, like I said, is we're trying to put in a real, more global illumination scheme, right? So I want lighting that has some more characteristics of real light than a simple directional point light. Directional point, that's good. Point light is not directional. Than a simple point light scheme. We're not, in this pass, trying to improve the quality of surface response. Remember, there's kind of two big parts of lighting that you want to think about. One is surface response, and that's how much a surface can represent like real world surfaces or different properties of real world surfaces, even if you're trying to be artistic, such as how glossy they are, whether they have anisotropic reflections, whether they shift the reflections, whether they have oily finish, whether they produce like the rainbow kind of a hue, right, from incoming light. Those are all properties of how incoming light is redistributed on a particular surface for the benefit of the viewer. And that is not what we're looking at now, right? That's the reflectance function, and we're not really looking at that now. For this game, we probably won't do much with that. It's not a game that cares about materials. It's hand-drawn artwork. It's cartoony. There's not a lot of room for, like, here is my oil finish chrome mech thing. Like, it's not that kind of game, right? But it is the kind of game where we're exploring interesting worlds, and it would be nice to have interesting lighting. So the part that I'm focusing on now is like the light transport part of things, right? It's the part where light is moved around the scene. And so we could do something relatively simple, which is just like the light that I've got here, right, that I'm moving around, where we just have a bunch of those. And that wouldn't be too hard for us to do. But that produces kind of relatively hard-edged stuff, as you can see, and isn't necessarily the kind of look that I want. It's more of the flashlight in a dark room kind of a look. It might make more sense in a horror game, not as much sense in a sort of fun exploration-y Zelda kind of a game. It's not, it just doesn't give that, I'm looking for more of the soft, redistributed light kind of look. And so it's the lighting transport that we're really looking at now. And what we decided to do was a harebrained scheme where basically I'm going to essentially treat it like a multigrid solver. Multigrid solvers are not traditionally used for lighting as far as I know. They're traditionally used for fluid dynamics. And the way they work is they try to treat things sort of like a MIP map. If you imagine that it's very expensive to get large-scale things to happen over a grid that's very fine. So, for example, if I'm trying to compute the lighting at every pixel, computing that could be very expensive. So what if I just do a MIP map process where I look at successively smaller versions of the lighting all the way up to like a single pixel encompassing the whole screen, compute the lighting progressively from there down and spread out the results so that at every stage I'm just computing some little local lighting, but I spread out large effects by having that MIP pyramid do sort of the work. The reason that I think it's a harebrained scheme and I really have no idea whether it's going to work is because light is not a fluid. And if there are theoretical physicists on the stream, I apologize for saying that, because for all I know, light is a fluid. I certainly don't want to pretend that I understand quantum dynamics, or quantum mechanics, I suppose I should say. I don't. However, what I mean to say is the lighting transport problem, as we typically look at in computer graphics, is not a fluid simulation. The reason it's not a fluid simulation is because typically the participating media is just not there. You're talking about light traveling long distances in a straight line, and you really don't have this sort of situation where you need to sort of diffuse energy the way that a fluid does, where fluid is only really interacting with the fluid directly next to it. So it's a harebrained scheme, multigrid, not really a great fit for it. However, one of the things that is true in general about lighting is that nothing is a good fit for it. It is a problem that defies any good solution. Monte Carlo methods are pretty much the only thing used at the high end for accuracy, and they are incredibly slow. So it's not like we're eschewing some really fantastic, perfect scheme that produces fantastic lighting in a short amount of time. That doesn't exist. So we are just looking for something that gives us an interesting, artistically pleasing result that bears some resemblance to how light actually works. That's all we really want. And so it's something that I think would be fun to try. Excuse me. All right. So there's two halves to this problem that we have to solve. One of them is incredibly easy, one of them is more difficult. The one that's incredibly easy is we have to get our lighting information down to the renderer in the first place, because up until now we have not had lighting, so there's no point in telling it whether things are lit up since nothing could light up. We are now going to have the ability for everything in the game to be lit if we want, and when I say everything, I mean literally everything. If this scheme works, anything in the game could be emitting light, no matter what shape it is even. So things like the entire cube that the hero is standing on right now could be lit up itself, and that would actually spread light around to the world. That would be awesome. Don't get your hopes up. Again, harebrained scheme, probably not going to work. So, with that in mind, that is one half of the problem. I think, I hope, I'm not sure, probably, I don't know. We can ignore that part of the problem for now, because all we really need is one light source to start practicing with to get the rest of the scheme working, and I suspect that will be the easier way to deal with it, because that way we can isolate the transfer problem where having to get lighting information out of our depth field passes will presumably be more difficult than just writing it directly into a buffer with its own separate pass that we can verify. So what I think I'm going to do first is take this point light source that we've got here and render that into the system to start with as its own separate, completely one-off pass that seeds the lighting for the lighting pass. And the reason I want to do that, again, is because I want to take the rendering of the depth peels into the light buffer out of the equation first. Because I feel like we could easily have bugs in that would lead us to believe the other part isn't working. So let's get the other part working as best we can first, with lights that we specify mechanically and precisely, so that we can set them to some place that we know, with a color that we know, in a very specific way. We can look at the bitmap and see that there is one light in the place we expect it to be at the start. And then we can look at each successive resolution of our multigrid up through the upward propagation and then the downward propagation to figure out whether what we're doing makes any sense at all or whether it's just dumb, right? Okay. And so the second part of that we have to deal with is the fact that we're going to need normals in this situation as well. And so that's a little bit harder to come by, but what we can do is assume that everything is pointing upwards at the beginning and just do the light transport with a flat surface and then work our way up to light transport with something else. So we have a lot of options here. We'll do the best we can. We don't know whether they'll work out okay, but like I said, we're going to take it one step at a time. And we'll see what we can do. All right. So let's get started. At the end of last stream, we already created some scratch space for this stuff to occur, and that was this thing called a light buffer. And what we did in the light buffer is we made a structure that would contain the things that we actually need. So we have 2 frame buffers here, right? I don't know why this is not called frame buffer. It should be, so let's go ahead and change that. There we go. So we've got 2 frame buffers here. These frame buffers are not representing different information. They're representing effectively the same information. Their only difference is they're representing different write styles. So one of the things that happens in OpenGL, and it's really annoying and stupid, but it's just the way that graphics cards work, and they have to do it for validation purposes because they don't have memory protection. It's a long story we don't need to go into right now, but it's just the way things are, is that you can't just point something at a texture and say, that's what I'm drawing to. Instead, you have to create this object that sort of slots textures into it and then gets validated. And so what that means is for every combination of textures we might want to write to, we have to create a corresponding frame buffer object and lock it down. If we don't, we run the risk of paying an extremely high upfront cost every time we switch to that writing scheme. Since we know that every time through the light buffer, we will only have 2 different lighting schemes, we just create a frame buffer for each of them so that the validation process can happen once and never again. That keeps us from having that hiccup. So that's why we've got these 2. So the write all frame buffer is the frame buffer that writes to these 4 at the same time. So there's a frame buffer that has these 4 as color buffers, which means that as we write in the shader, we can actually emit one thing to each of them. The point of that is on the upward process when we gather our lighting up and we successively smush it down to smaller and smaller resolution texture maps to do bigger and bigger transfers. We want to be able to average all of those together at once. We want to take basically a set of 4 pixels, smush them together, and write out 1 pixel in the lower res map every time we take that sampling down 1 step. So that's really what that is for, what the write all frame buffer is for, is the upward sampling process, which is producing coarser and coarser averaged versions of the lighting. The write emit frame buffer is the way down. So once we have that, we know that the surface colors at any point and the x, y of the direction and the depth at which the lighting surface is being considered for any particular point, those are not going to change anymore because we're producing them whole cloth on the way up. Because remember, we basically start with empty textures all the way in our MIP period except for the base level, which is the one that initially has the lighting written into it. So what we need to do from there is condense those and create the new ones. That's why we're writing everything. On the way down, we don't need to touch the surface color or the position or direction of the surface elements because that's just known and it doesn't change. The reflectance properties of a surface aren't going to change, right? They're just known now. So now we've built the MIP pyramid, it's done. What's going to change is the light transport. So what we do on each step down the pyramid is we take a look at what the emitters are nearby, and we add in light to the front and back of the particular element that we are considering at the next level down, right? And more specifically, we do it for a couple different ones of them, right? And so that in and out process, like I said, because it's writing very different things, we create 2 frame buffers because we don't want to blow a bunch of writes on the way down for no reason. Because remember, we're going to want to optimize this eventually. We're going to want to make sure that we're not spending a bunch of bandwidth unnecessarily. And if we just wrote the surface color texture in the MP text again, or even just flushed zeros out to them, it's just bandwidth we don't need to spend because those textures only need to be read from. They don't need to be written to at all. And so that's a really important part of the process to understand. Okay. And also I should mention one other thing. It actually also gives us a feature that we might want, which is that the surface color texture and the NP texture for the lower level version is actually something that we could read from in the same stage, right? And that's a sort of thing that I don't actually know yet. It may be that we actually need 2 more textures in here, right? We may need an emit up and an emit down, and the reason is because we need to read from different ones that we write to potentially. And so that I just don't know yet. I'm not sure. I think we might. And we'll see when we write the code, it'll be obvious. But the reason that I say that, just to be clear, is the way that this thing is going to work is essentially, you can imagine us looking at these bitmaps, right? So here we've got a 2x2, and here we've got a 4x4. So in any particular stage of this algorithm, we're going to be looking at 2x2s that expand to 4x4s, more or less, right? And what we're going to be doing to you got to kind of think of it, I suppose, as being a whole grid as well. But what we're going to do is we're going to say something like, well, we need to update the lighting information for this cell, right? And maybe what I should have done is said we're going to update the lighting information for this cell, right? And in order to do that, we would say, well, what's the bilinear sample that takes place like right here? Because that's where that cell maps to in the upper level bitmap, right? And so in order to do that, we're going to look at these 4 cells worth of lighting and compute a lighting adjustment for this. But it's a lighting adjustment, right? That's the important part. It's going to adjust the lighting at that point. It's not going to overwrite it completely. It's going to do a plus or minus. At least that's my assumption. We'll see when we start experimenting. So what we can do is we could write an add to it, and if it's floating point and supports floating point add as a blend mode, then we would be able to just let that happen. But if it doesn't support that, if it doesn't support floating point add as a blend mode, which I don't know how many cards do, then we need to read from this texture to figure out what was there in the first place so we can do the add and then write the result out. If that's the case, we really can't read from and write to the same texture in the same pass, right? That's not allowed. That's why we have a blending unit. If you could read and write from one texture in the same pass, you wouldn't need a blending unit, right? There'd be no such thing as blending. Because if you wanted to blend with the result, you'd just set the destination buffer as one of your input textures. It's a much cleaner way to do it, much more powerful. Problem is it's much more expensive because now everything has to be serialized. So that's why we have a blending unit. So if the blending unit supports add, great, I think we're good to go. If the blending unit doesn't support add, I think we're going to have a separate texture that we write to. So basically this right here would be, GLU and, final front emit or something, right? I don't know. But it would go down in that way. So again, not a problem at all. We don't care about that because it doesn't increase our bandwidth much at all. Because again, we're not reading and writing from another set of bitmaps. What we're doing is substituting one of the places we were writing to with a different thing. So while it could affect the cache a little bit, since these are passes, I don't think it would because they'd probably be out of the cache by then. I don't know, maybe at the top of the pyramid they wouldn't be, but it's hard to say. So chances are this wouldn't affect us too much, but again, you never really know. Obviously, if we can do it with less textures, we should because it can't hurt. But again, like I say, it could be the case that we need to add them there. I'm not concerned about that. It's not as bad as having to add more that we're actually using at the same time, because that's the thing that we really want to try and keep down, because we're already pretty high here with 4 textures at the same time. It's a lot of textures to write to at the same time. And keep in mind, it's gonna get worse. Those 4 textures could expand to 8 textures or 16 textures eventually, depending on how we choose to do the depth peeling. If we choose to smush the depth peeling down into a volume texture, or a texture array, where we just have one texture that has 3 levels, that's probably the smartest way to go, and that's probably how I'll try to go. And in that case, it'll always just be 4, and we won't have to worry about it. But if we choose to have those be separate textures, that becomes a little bit more complicated. The reason it becomes a little bit more complicated because at that point, we've got just a lot of texture handles sitting around. 16 is the maximum we could probably expect to use. We would be using that maximum. That doesn't thrill me, right? I don't like to be up at the maximum number for anything, if you can avoid it. But, if we have to, we have to. So, my suspicion would be, these will probably expand to volume textures or texture arrays probably. They don't really need to be volume textures for any particular reason. in the sense that we don't need to look them up by arbitrary UVW. What we really just need to be able to pick a 0, 1, or 2, or 3. We're going to read from each of the frames successively. So a texture array would be fine for our purposes. All right, so anyway, here we go. Let's get started. We know what we need to do. It's just going to be a bit of a grind to do it. And again, it'd be pretty easy to just write this code, but in GPU land, it's gonna take a bunch of gyration and happy dances and weird shaders and all this other sorts of thing. So okay, let's start out by creating a very simple process. What we want to do here is create a shader that's going to write a light source into the base level map of one of these maps, and then draw that to the screen. So we just want to draw it to the screen so we can see it, so that we know what it's doing. Because if we can't see these things, we're never going to know if they're working right. So what I want to do is I want to be able to look through those different parts of the map. So in addition to that, what I'm also going to do is I'm going to do something nuts here. We're going to have a totally nutso crazy situation where inside the OpenGL renderer, I'm going to let us pick out what we want to view so that we can view each level of those texture maps in series as we go. So what you can see here is at the end, we kind of had this thing that we were using before where we were like, here's a blit frame buffer, right? We want to look at what's in this frame buffer here, right? So what I'm going to do is I'm essentially just going to hijack this code and turn it back on so that we can view our frame buffers directly at the end, looking at exactly what they look like, right? And I don't really remember if this does a stretch, but I believe it does. I don't know that we really want the stretch to be changing our pixel values. So what I'm going to do is I'm going to set it to nearest neighbor sampling so that we can actually see the big old pixels. Because for this, we really want to know exactly what's getting written. We're not looking to produce a visually pleasing image right now. What we're looking to do is verify results. And so I don't want any adulteration of the pixel values. I want to know exactly what they are. So then what I'm going to do here is I'm going to say, well, we've got a light buffer, right? And we've got 4 things in the light buffer, right? We've got the front, the back, the surface, and the NP text, right? So what I want to do here is I want to basically blit those various things to the screen separately. And I guess now that I look at it, maybe I don't really want to use the frame buffer blit though, because that would only allow me to display one thing at a time, right? Because I can't blit. I mean, I shouldn't say one thing at a time. It would only allow me to display the color buffer 0, right? I don't know if GLBlit flame buffer allows me to go from one frame buffer from one attachment to the other. Let's take a look if it does. If it does, then I'll use it. If it doesn't, I'm going to use an actual texture fill, because then I can pick out whichever texture I want, which is what I'd rather be able to do. So let's take a look here at GLBlit frame buffer, and let's take a look at what it's going at. It's the bitwise overflows. Okay, color buffer bit. Does it say which one it does? It does not seem to. It does not seem to at all. Let's see what happens if I say I'm just curious if anyone discusses this. So you can do it, it looks like. Okay, so we can actually pick out any one we want, so that seems fine to me. I'm fine with that. So all I really need to do is keep that blitting, and what I can do here is insert a GL read buffer call, where GL color attachment, right, gets added something can add to that where we pick out which one we want. So what I want to do here is when we're viewing these, I want to basically be able to say, okay, bind the frame buffer, whatever the light buffers that we want here. Let's call that buff index. And I want to go ahead and get the right all frame buffer because that's got all 4 of them in it, right? And what I want to do there is say, okay, I'm going to read from the write all frame buffer for whatever light buffer we chose. I'm going to read out of its whichever index, 0 through 3 here. We're going to set the viewport to be whatever the viewport actually is that we can see, and then we're going to blit out whatever the size of that buffer was. Now, unfortunately, figuring out what the size of that buffer was is actually a little bit annoying. What I might do here is just store those values, right? So if I wanted to know how big each light buffer is, that's actually kind of annoying to figure out because it's a successively sampled thing. So when you're on the nth one, you'd have to be tracking what the original size was and all these other sorts of things. So instead of that, what I'd rather do, I guess, is just have it so that we say, like, okay, which one of these are we on? Which one of the buffers? And then what I'll do is I'll just say, well, we'll look up what its width is in the buffer itself, and I'll tell it. So what I can do there is say, like, hey, let's go ahead and record that when we're actually initializing. So in here, we obviously know it here, right? Because we've got the text width and the text height that we've computed by using the sort of successive divide process. So what I want to do here is say, okay, the text width, oops. The text width and text heights will be stored, so those will now be known. Then what we do is we can do this blit, and that will give us a full screen view of what the buffer looks like, whichever one we pick. And so for the moment, I'll just set them both to 0. And so when we run this, we should just get a black screen, right? Because even though we're rendering the game, right, and if I were to make this an if0, the game would just render. Immediately after rendering the image of the game, we're going to just blow right over it, just overwrite it with whatever's in that buffer. So now, when I write to that buffer, I'll be able to see what is there, right? I'll be able to see what's actually going on. So one thing I'm not sure about, again, I am assuming that GL blit frame buffer will do the right thing and convert floating point to 8-bit. I'm assuming. If it doesn't, we have a problem. We're about to see whether we have a problem, so off we go. So let's start, again, let's start simple. We need to start by prepping this frame buffer. And so what I'll do is I'll just make up some dummy things here. I don't really want to be on that side of the screen because my head's in the way. Let's start, must be over here. What I want to do is I want to have some functions that I can use to get this lighting started. So probably what's going to happen, right, is we're going to draw a bunch of stuff to the lighting, like the lighting prep will happen. So let's do fake, fake seed lighting or something. So we'll seed the lighting with something completely arbitrary, like one little light source. And we'll let that happen. Then we will go ahead and run the actual lighting equation. So then we'll actually do like light transport or compute light transport. And again, all that has to do is just operate on the light buffers. So the lighting happens entirely in these buffers. Nothing else has to occur at all. So we're kind of okay at that point. Everything happens in there. Then we'll draw one of the buffers out, right? So our job is to write these two things. So let's write them. Here's fake seed lighting. Here's compute light transport. And compute light transport is just going to be like I assume it's harebrained like the rabbit, or is it harebrained like the follicle? Who knows? So this we don't care about just yet, because before we can do any lighting transfer, we have to have some lighting in the buffer to begin with. So what I want to do here is I want to do fake seed lighting to put something into the lowest level buffer, buff 0, to seed it out, right? So I want to fill the world with a fake version of lighting that we can play with, right? In order to do that, I'm going to write a shader. That shader is going to try to write to those 4 textures, and it's going to write some procedural geometry that we make up in the shader out to those things, right? And again, the whole point of doing this is because I want to isolate these processes, because I'm anticipating having to do a lot of work to get this lighting to behave correctly. And I don't want to worry about the transfer of things yet, because that will just give me this huge complexity at the beginning that I don't need. I want to be able to make a shader that just produces something simple like a sphere, right? And check how that well understood thing is behaving with the lighting before I try to go, okay, now we've got the actual handmade hero geometry coming from death peels and how does blah, 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 right? So nice 2D, simple lighting transport, nothing weird happening first, and then move it up. All right. So this is going to be something like this, right? In order to do the fake seed lighting, we actually don't need any active texture units. So we're just going to use like a fake seed lighting, use begin and program thing, and we'll go write that program, right? That's the program we have to write. In terms of what we want to draw, it's basically the same as this stuff right here, right? There's really nothing else to it. In fact, you could argue that we could just pull this out entirely. In fact, let's do that. Not a great name. But this is what I want it to be, right? So it would basically be you give it a frame buffer handle. And then you give it a width and a height. And it would just take it from there, right? And then you know when you come back, you're all good. So I think we probably want to do like begin screen fill, maybe. End screen fill, something like this. Because this has to get in there as well. You know what I'm saying? So let's take this out for one hot second. Just a hot little second. And when you do OpenGL begin screen fill, end screen fill, I'll just test it out with what we're currently doing to make sure it still works. So that's good. And then fake seed lighting can do the exact same thing. So we're going to pretty much only write in the fake seed lighting, we're only going to write to the base level because everything else will be filled in by the lighting transport process. So we really only need to write to that bottom buffer. That's the only one that we're going to write to. So in order to make that work, we just need to pick out which one of these we're going to use. We want to write everything, so we're going to call it the write all frame buffer at this point. The width and height are specified inside the buffer itself, so those are not a mystery. So that's pretty much everything that we need to do there. Now again, what I'm going to do here is I've turned off a call to that because I want to make sure that that code still works, and it looks fine, so that's good. And so now we can turn it back on. Okay. So this is all we really need to do. I'm confused. Where's, there it is. I'm like, that wall of text, I kind of think maybe it needs to be a little clearer. There we go. I'm like, what am I looking at? There we go. So all we really want is this GL draw arrays here. That's all we really want. And so in this case, I suppose we could probably do that because we don't really have anything else to look for. But so that's all we need to do to fill the screen with something. And so all we need now is we need to actually write an all, I guess, since this is a lot of work. But yes, all we need to do now is have an actual shader that will write something into this geometry. Now this is going to be fun because we got to go look up the GLSL that I never remember for outputting to successive render buffers. I don't remember how it corresponds output colors to output textures, to color attachments. I can't remember whether you need to use a specific array or whether it just lines them up in the order they're declared. Being GLSL, it's something weird, as always, but we just need to go look up what it is. And then we should be good. All right, so moving along. Before we do any of that, of course, we have to actually create something to compile our texture. So let's go hunt for some texture stuff here. We probably want something like our multi-sample resolve because the multi-sample resolve, I think, yeah, as you can see, it's the kind of thing we want that's just based on the text chord. Doesn't take much in. So let's just grab this multi-sample resolve program and let's go ahead and make ourselves a new version of that somewhere here. There we go. Okay, so we want this to be compile fake seed lighting. And this is going to be our fake seed lighting program. And yeah, I don't know that we have any defines at this point that go in here because it doesn't use any of this stuff that you would normally need. It's kind of just the version number. That's it. The vertex shader does nothing, as always. And so in this case, for the fragment code, it wouldn't be sampling from anything at all. It wouldn't have any defines or anything. So we're literally just looking at just the basics here, like so. So what I'm going to do here is just try to figure out how to write something to each of these buffers, right? And what I'd like to do is essentially do something like this. I'd like to make sure that each buffer is getting targeted as I expect. So what I would like to do is something like that corresponds here. So we say, okay, there's the front emit, back emit, surface, color, MP text, right? I would like each of these to be writable, and I would like to write something to them that I can identify. So this is just structured artwork, folks, right? It's just saying, hey, I want to know that I'm targeting each of these bitmaps properly, so I'm just going to output red, green, blue, and yellow to each bitmap so it's just filled with that color. That way, we can then verify that we're at least writing to the buffers we think we're writing to. basic stuff for step one. And again, what we'll have to do here is go look up the GLSL protocol for targeting multiple color attachments. We have not done that yet on Handmade Hero, and obviously we need to do that, and I don't remember what it was. So, that's all we should need. There are no variables to this shader at all, because it's just creating geometry from whole cloth. We probably will want to specify the light. So I am going to go ahead and copy the lighting stuff out of the depth peel sampler because we want this debug light P. We want to specify the debug light P because that way we can move the light around. We're not going to do anything with that just yet, but we will eventually. So I'm going to, in here, I'm going to have a uniform vec3 light P, and that'll just be where the light is. Right? Again, only reason for that is so it'll move around with the hero. So once we've got that going, now we can compile the fake seed lighting. The fake seed lighting program, again, doesn't really have very much in it. It's pretty straightforward. Let me go ahead and cut this out here. I'll put that in there. So this is just fake seed lighting. And all it's going to have is just the debug light P. That's it. Pretty boring. And so then down here we've got that actual one, fake seed lighting. Fake seed lighting. And when we actually compile our programs, right here, we also, I think, free these up at the top here. Let's see, 1, 2, 3, 4, 5, 6. Yep, we got all those guys in there, and that's it. Okay. So that should actually compile the lighting. And so now the only thing we need to do is actually use that program. We're already calling use program with it. So then we just need a thing that does use program to bind that one variable. So when we look at this guy, that should be basically everything there is. So I think we just need to pass that setup to it, and that should be all there is, I think. We need to keep that light P around, though, which makes it a little bit trickier because this is happening kind of in a debug location, but that's okay, that won't be too bad. So looking at that, again, we can just delete all of this because that's the only thing that needs to be there. So now when we do use program begin here, what we need to do is have some way of passing that render setup down. Now, what we can do in the meantime is just capture it out of the render texture quads like the first one. So, you know, here where we do setup, we could say if not debug setup, we could just say debug setup equals setup. To do KC, remove this. And then all we need to do is just cache this. And so this is just taking the first one, right? I don't remember what this was defined as. Just a render setup. So you can see there I've got this debug setup thing. I'm going to set it to 0 initially. I'm going to go and set it when we see the first one. And then at the end, I'm just going to use that, right? That's the one that I'm going to use. I'm going to check to make sure that we've got one of those, and if we don't have one of those, then we're not going to do anything. But that's about it. So let's see. What did I not do that? Probably left it defined as Z-bias program. There we are. And fake seed lighting. We go. So in theory, that will run the fake seed lighting program. In theory, it will have access to the debug light, and in theory, it will show us one of the buffers. Now, what we're seeing here is actually already kind of interesting to me. I don't know if it's interesting to you. But we see a green screen. What's interesting about a green screen is if we're looking at the first texture, right? remember what happened when we created these. So if we look back, and maybe I'll put it up on this one. So when we do our OpenGL init, not our OpenGL init, our change to settings. When we do our settings change, you can see we create these frame references. We attach, attachment 0, 1, 2, 3, and you can see like front emit tech is the first one, right? And so if I go down here and I look at our fake seed lighting program, you can see that front emit is the first thing we write to, but we wrote red. Yet when we view frame buffer 0, texture 0, that's not what we see. We see the back emit, which is actually color attachment 1, right? So I'm going to just double check that we're actually picking out the read buffer properly. But I think we are. The other thing I need to probably do is make sure we restore that read buffer in case anyone else was counting on it. But yeah. So I think what that suggests to me is, again, that there's probably some protocol we have to look up in GLSL to tell it where to write to, because it's not just writing them in the order that they were declared, right? Which I'm not suggesting that it should. That's not like something it should be doing or anything. I was just saying if it did do that, we would have expected to see red, not green, coming into that first texture. Unless there's some other bug somewhere else, right, in the program, which there might be. All right, so here we go. GLSL, run a quick reference card. For the benefit of folks at home, let's go ahead and zoom in on that. And so what we want to do here is we want to go down to the OpenGL shading language 1.5, which is what we were currently using, I believe, and see if there's a way to target multiple outputs from it. Hopefully there are. Hopefully we won't have to bump the shader version to do that. So taking a look here, you can see we've got in our fragment language, right? There's an outfloat for the frag depth. There is no outfloat anywhere for the color, or out vec4 for the color. So I'm not sure exactly, again, that this is going to tell us what we want to know, right? I don't see anything here. Excuse me. I don't see anything here that suggests what goes where. So I think that should probably drive us over to the spec. I don't want this one because that's a little bit too late. Where is the spec page? Here, there it is. So we want probably OpenGL 3.2 shading language 1.5. There it is. And so when we look at this, what I'm trying to get to as quickly as possible is just something that tells me how to line up my output fragments with the bound color attachments for the frame buffer. And so I don't know where that's going to be exactly in here, but we can take a scan through the table of contents and see. It's really just an overview. Okay. I guess one question is, can we write to more than one at once? Maybe we can't, which would be bad. Fragment series output values to the OpenGL pipeline use the built-in GL frag color, frag data, frag depth, unless discard. Oh, well, this suggests that it was already deprecated. So If it's already been deprecated, there must be a way to do it in this new language. So what's the new way? Pray tell. Both GL fragment and GL deprecated. The preferred use to explicitly declare these outputs in the fragment shader using the out storage qualifier. Does that mean I just declare one of those? Writing to glfrag data n specifies the fragment data that will be used by the subsequent fixed function pipeline for data n. That's all I really want. So can I do that? Wow, typing is hard. Let's go shopping. All right, so what we need to do here is just say at the end of our situation, nope. Here are our buffers. We are writing to them 1, 2, 3. We've got front emit, back emit, surface color, mptech, and we'll see if the shader compiler likes it or if it thinks it's bad. Hey, looks like that worked. So now what I'd like to do is, now that it sort of looks like we're writing to our frame buffers properly, each of those kind of getting the value that we expect, what I'd like to do is actually double verify that, and of course we're going to need this for the next step, which is actually doing something real with the fake lighting, real fake lighting, is I want to be able to interactively toggle between which one of the things I'm viewing, right? So I want to be able to both step up and down the MIP chain, and I want to be able to change which texture I'm looking at. The front, back, surface, emitting, whatever kinds of things. So I'm just going to hack in something to the OpenGL here that allows me to do that. Because normally the OpenGL layer doesn't really have any notion of that. And the external code has no way of poking at that, but I'm going to let it. I'm going to let it poke at that. So what I'm going to do there is just say, like, okay, let's suppose that our lighting buffer, maybe this is something that can be edited in the current settings or something like this. So maybe in the platform layer, right, here's the settings. What I could do here is just say, like, okay, in addition, what we could say is like debug light buffer index and debug light buffer text index, right? And these two could be something that the OpenGL layer picks up if they're set to something like so. Do we get past the settings here? Where it's actually not that way. It's actually command settings, right? Yeah. I wonder if we should just do this. All right. Yeah. Let me just let the compiler bring me to the correct line. Thank you. So once we've got that set up, we are free now in any part of the code to push that around, right? And oh, I suppose I should make sure it's cleared. Is it not cleared first? Are we not clearing that? Let me verify that that's actually what happened. That looks like that's not a cleared value. Yeah. That's not a cleared value, apparently. Why is that not a cleared value? Dare I ask? So, Now what I can do is introduce some debug keys pretty much anywhere I want. They could be in the game, they could be in the platform layer that basically let me kind of swizzle around between those. Now the game itself, if I remember correctly, doesn't really get much in the way of debug keys. The platform code, if I remember correctly, just gets like what the state of the controllers are and stuff like this, right? I think, let me see here. Yeah, so it doesn't really get that kind of stuff. So what I'm going to do is I'm just going to put it in the Win32 layer for the moment. What I'm going to do is just say like, okay, wherever these are getting set. Oh, you know what I just realized? That's not a good place to put it. I take it all back. The settings are things that affect the compilation. And that's not appropriate for that purpose. These are compilation values. So that's really not an appropriate place to put that. So we really should probably put those in here. Okay. So now what I want to do is inside there, I want some way of poking at those values just randomly. So what I'll probably do is say, like, okay, when we access the keyboard here, maybe I'll just give myself some ways of getting some debug keys. And here, you can see we've got some kind of weird stuff, like the loop live code editing still being taken care of there, for example. And so what I want to do is I want to put some extra ones in here that I can use to control this. So what I'm going to do is I'm going to say like, okay, VK code in this case, let me use like plus and minus, I guess. And maybe I'll just use plus and minus with the shift key down or not. By the way, someone wrote in a bug that was a good bug to write in that had to do with sign extension for this gentleman right here, which we do need to fix. It's kind of interesting, so I don't want to fix it yet because I'm pretty sure I put it on the GitHub and I wanted to talk about it. Let me just make sure that it's on there. I'm pretty sure I put it on there. Yeah. I want to talk about that one in more detail. So we're not going to fix it right now. We're going to fix it when we look at that bug because I wanted to talk about it in a little more detail. But what I wanted to do was take a look at the shift key was down. I feel like that's an L param that comes in through WM key down that we can just check. Let's find out. Let's see. Is that here? It does not appear. So I will probably use get key state then. I don't want get async keyed state, and I don't want get key state actually. Do I? I just want regular get key state. That's what I'm looking for. Thank you. So I just want a thing that tells me whether the this key is down or not. with the return value, if the higher order bit's 1, the key is down, otherwise it's up. That's the only thing that I really need to look for. It's a short, so it's going to be bit 15. Did we do this get key state somewhere else? Yes, it's right here. Of course, it's behind my head, so I couldn't actually see it, but oh well. So if we want to know if shift is down, we can do this. I'll put this up at the top so that anyone can use it. Here's shift key was down. So we'll look at VK shift and whether 1 shifted up 15 ands with it properly. If it is, then the shift key was down. So in here, we can just look to see if the shift key is down. So this is the plus. So what I want to do here is say, well, the OpenGL layers debug light buffer index plus equals 1 in this case, or minus equals 1 in the other case. I think I'm probably going to want these to be S32s so that it can wrap properly. And when we come through here, what I'm going to do is say if OpenGL debug light buffer index is less than 0. In fact, you know what I'll just do? I'll just do this. I guess clamp 0n is really what we need here. And so we want this to be something that goes from 0 to the number of light buffers we have. And in this case, that is specified in the actual OpenGL settings itself, if I remember correctly. It's this light buffer count. And this, it has to be between 0 and 3, right? It actually has to be light buffer count minus 1. That's the maximum value it can be. And I guess in this case, we can do this as well. So yeah, if I do that clamping here, then we know that those will always stay within bounds no matter what happens with the other parts of it, right? And then when we grab these out here, we grab out the indices and use them. We can actually avoid probably ever actually doing this because we're always going to be doing it just to pull them out one time, like so. So we can probably just do that. And then we just need to write the clamping function, and I think that's the only thing left to do in this case. And then we can view any level of the texture and any subcomponent of it, which is what we need to do for the debugging purposes. All right. So let's go ahead and write this clamp function. You can see right now we've got one for real values, but in this case we want one that's going to work on S32s. It's the same function. You could probably use a template for this. I don't see any particular reason why you couldn't. Or a macro. Okay, and so in theory now we can like bump those values. So actually, let me just make sure that before I do that, I just wanted to look at this one more time. This was not what I wanted. It should actually look like this. Anytime you hit the plus key, it should add. So it should really just be which one you're looking at. I think I probably want it the other way around, actually. I probably want it so that plus and minus moves up and down the levels of detail. And then if you hold down the shift key, then it changes which texture you're on, right? I think that's what I want. That looks surprisingly ineffectual, or feels surprisingly ineffectual, I should say. All right, so let's take a quick second to debug this. Let me go ahead and run. Now what I'm going to do here is I'm going to hit plus So now I should have moved to a new frame buffer, which means there should be nothing in the frame buffer, and I shouldn't be getting that blit, right? So now if I come through here and take a look at it, I want to see what the light buffer index is, and it's still 0. So something's busted there. All right, so if I hit the plus key or the minus key, all right, so I'm not actually getting anything there. Why am I not getting anything there? Is Handmade internal not set for some reason? Win32 process pending messages, switch message. If we get a key down message, it should come in here. If was down is not equal to is down, then we should process these, which should include the P, the L, the equals. Oh, you know what? Do I need to use a VK code for this? Let me look at the Windows VK codes. I'm not sure if maybe you can't use the ASCII code. Because it looks like we're coming through this path. We should be coming through this path, okay. But it doesn't look like we're actually getting it doesn't look like we're ever actually able to match the VK code of equals or minus, which we should be able to match, I would think. Just to verify that that's true, I'm going to set it to, instead of plus and minus, I'm going to set it to 0 and 9, just to see what happens. So yeah, so those must just be VK codes that don't line up with the ASCII. So let's see what those actually are. We should be able to do that using like the test project pretty easily. So if I just go over to our stupid test project we made, go ahead, flog those hamsters, Visual Studio. All right, so if I do VK underscore, I should see, well, okay, there we go. I should eventually see an autocomplete that shows me all the VK codes. So I would have thought there was like a VK plus on here, or a VK equals. Again, I don't know if there is. Let's see. Nope, maybe not. But either way, let's say I pick VKR control and I do a go to definition. Here is the VK code definition table. You can kind of see it all happening in here. And they don't define anything that lines up with ASCII code, so those are gone. So it's only like ones that you have to use specific VK codes for. But I don't see it on there. Well, I guess one thing we could do is just see what the VK code is when it comes through, right? I mean, that's easy enough. So if I switch back to our other project, what is it? No, I don't need to save that, but thank you. So if I go ahead and just run the program, right? Here's the program. So and I hit the equals key. And so what's the VK code? 187. So what's equals and what's plus? So equals definitely comes through as a high key code. It comes through as 187. Let's see, are they defined, so 187, are they defined in hex? Oops, almost knocked over my coffee there. Well, actually I did knock it over, but it's spill proof, thankfully. So it's 187. They're in hex. Hello? There you go. So we are looking for BB as a value, right? And so what would that be? So it's VKOEM plus, apparently, is what we're looking for. And I guess by that logic, we're also looking for VKOEM comma. Don't ask me why. That's just the way it is, I guess. Oops. That's not what I wanted. So now plus and minus should work properly. It does appear to. And shift plus does not appear to be working properly unless our output code is busted. So let's see here. Debug lightbuff text index. I'm going to go ahead and set a breakpoint there and see if that is working properly. So let's see. So that is adding debug lightbuff text index plus 1. There it is, right? And so what I should be able to do now is go take a look at what happens in this code. The lightbuff text index is 0. The text index is 1. So by setting the read buffer to GL color attachment 1, we would think we'd be able to read out of that buffer and blit it, but it doesn't look like we are because we're just getting a black screen. Now, what we don't know is we don't know who is at fault here, right? We don't know whether the read is failing to target the correct texture or whether the write is failing to target the correct texture, right? We have no idea which of those two things is true. So if I go over to our OpenGL code again, at least we know we're picking out the right things. So if I go over here and I want to take a look at what we've, what we're actually doing for our write, I don't see a lot of ways that this could be wrong unless we're misinterpreting what they meant by defining the GL frag data to be 0 to the number of buffers, because it's pretty straightforward. It's an outVec 4. It's an array of 4. So I guess there's a couple things I don't know. When outputting to multiple frame buffer color attachments, I don't know if they have to be GL enabled. So let me take a quick look at that. Frame buffer has a table of draw buffers which are indexed on the half open range to max draw buffers. The frame buffers table maps from these indices to named color buffers in the frame buffer. What? So wait, you're telling me you double bind these? Why? What is the point of that? So basically, we have to set GL draw buffers from 0 to the number of buffers. We have to set that separately in addition to having bound the buffers. The values in bus must name specific color buffers frame buffer for the default frame buffer buffer names. What is the point of that? Okay. Like, wouldn't you just create another frame buffer if you wanted to swizzle? I don't understand. GL always has such weird legacy stuff in it where you're just like, what is the point of this? Why do you introduce indirection after indirection after indirection? All right. So, yeah, maybe that's all there was, that we have to specify the additional mapping table, which... do we have to specify that per frame buffer? I don't know. Who knows? Anyway, let's assume we have to specify it per frame buffer because it sure seemed like it was associated with the frame buffer object, making yet more work for the driver, of course. So let's go ahead and take a look at the settings change code where we actually create these frame buffers, and then I'll just call GL draw buffers with this code. So in this case, we want 4. In this case, we want 2. And in either case, it's just going to be this all the time anyway. So cannot convert from GLenum, only initialize your list with 0 when elements converted to this type. That's a good point. I see your point. And so that GL drawbars call must be also an extended call, I guess. Core arb draw buffers. Yeah. All right, here we go. Make sure this is exactly what we want first. All right, so that looks like what we want. So we'll put it in here, and we'll just cross our fingers. So if I want to put that in there, what I need first is I need a definition of it somewhere, right? So let's just stick that in there. Here's the type def. And then we need to do the little dance of acquiring it. So we run, and we're calling it now, and we didn't get an error, so that's nice. But we still don't know if it's working. Ah, very nice. Unfortunately, it looks like we're getting multiple pulses on that. So I would like, I don't know if that's just that may just be a keyboard glitch, or it might be because we're accidentally setting like the read buffer and then that changes how things behave later or something like this. So let's just make sure really quickly that we're properly handling the pulse there. So in OpenGL, in Win32 Handmade, where we actually check that OEM plus. So in here, I think we want to make sure that this, I guess we want was down, we want to make sure was down and is down. Does this, so I don't really know exactly. Let's take a look. Maybe this actually could be related to the bug that we were supposed to fix, which I could discuss now as well. Let's just take a look at what that is down tends to be. So let's just say we have test out, and I do a with sprintf, and I say like is, was, is, and I just do a %x, %x. Or actually, I do. Something like this. So this is just basically shoving it out the debug port so we can take a look at it. There we go. And I'm going to run it. So now what I should be able to do is take a look at what that happens to be. So 0 is 1, 1 is 0, 0 is 1, 1 is 0, 0 is 1, 1 is 0. That looks like what we would expect. Let's run it in windowed so I can watch it happen as I click. So here's the output. So that looks correct to me. That's good. Oh, but you know what? It's going to happen 2 times because for all of these things here, we actually want like these to happen only on is down. So I guess in this case, these should actually be moved into here. Right. So now let's take a look at this a little bit more stable. There we go. So now we can look at every texture in series, and we can also look at every level of every texture, right? So that's great. So now that we have the ability to debug that, what we want to do is now try writing some fake lighting into a bitmap. And again, this is just to set us up so that we can start this process of debugging the lighting transport, because I'm going to write some stuff into a shader, and there's going to be bugs in it, and we're not going to know what the bugs are or how to fix them unless we can see very obviously what's in those textures. And even then it might be a little bit hard, but we'll do our best. So what we want to do now is we want to go ahead and look. We've got compile fake seed lighting here. This is our code. So what we can do here is we can start by putting in to our front emit and back emit. We can start by putting in some sort of information that we know to be plausible. So what we know about, for example, our nptex, and also one of the things that we know about all these frags is I guess they don't have an alpha value. So I don't know whether that means I should output vec4s still because the shader would like to see it that way, or whether I can just output them as vec3s because there's no alpha value. So I guess before we do anything else, maybe I'll just go ahead and do that. Let's find out what happens if I change these to vec3s. Does the shader accept that, or do you always have to output an alpha value? Right. So it looks like the answer is it needs to be, oops, well, no, it could just be that. So it looks like maybe I can do that. I'll let the internet at large tell me whether I can or cannot as other people test this on other cards, which they often do every night when I post the builds. I don't know if that's actually legal or not, but this is what we're actually doing, meaning none of those textures have an alpha channel. So I don't know whether OpenGL would be happier with me explicitly saying, here are the RGB values, there is no A value, or whether it would like to always see an A value and throw it away. So I don't know which of those is more appropriate. But for now, we'll just stick with actually generating what we actually have, which is this. There are no alpha values in these textures. They're just RGB textures. So now when I go to write this out, we've got a front emit and a back emit. We've got a surface color and an MP-Tech. So what I'd like to do here is I'd like to go ahead and start playing with these values and put some things in that might be sensible. So what we said we would do, remember for our encoding in here, is we said that it would be NX, NZ depth, right? What I'm going to do is I'm going to leave the depth value at a constant and the NX value at a constant for most of the places, and only where we put the light source in will I change them. So what I'm going to do for that is I'm going to say that the default value for all of these is something that does not emit any light. The surface for now will just be colorless. It'll just be gray. That reflects the light that comes back to it. Let's say it reflects the light that comes back to it at 1/7 of a value. One thing that you have to be careful about, let me just throw this out there right away. As we start moving towards more physically accurate lighting, and by physically accurate, I'm putting that in huge quotes because we are in no way trying to be physically accurate with the lighting. But all I mean by that is as you start adding more elements of physicality to your lighting, you reduce the ways in which you can set your parameters. So for example, we are now adding the concept that light gets transported around the scene. Once you allow light to get transported around the scene, a value of 1 for reflectance is no longer plausible. There is no such thing as light that bounces around forever. So you will start to get subtle bugs in the lighting that have nothing to do with the lighting transport that are actually just because your values are physically implausible. So once you bounce light around a scene, it's important to respect the reality of the physicality of light, which is that there are no objects in the real world that you commonly observe that bounce 100% of the photons off them. They all absorb a little bit. So even the brightest white paint in a room bounces photons at like 90% or 80% or something. It doesn't bounce 100% of the photons. That's why your room isn't infinitely bright, right? If all the photons always bounced off all the objects all the time, every surface would be as bright as the light, for the most part, right? That's not actually true. But they would be a lot brighter, let's put it that way. Every surface would be a lot brighter because you would never get any absorption. So when you look at a particular part of your wall, what you would see is the inverse square law from the light source and nothing else. It would just be that. So everything in your room would be like a uniform brightness. There was just inverse square law and cosine angle, and that's it. You would see no other diminutization of the light source. So something that was in shadow would not really be in shadow, right? It would be still bright because light would get there eventually because it's not getting absorbed by anything, right? So even though you would still see, what I said initially was way exaggerated. It's not true. You would not see everything would be as bright as light source. But what you would see is no real shadowing, right? Because things wouldn't be absorbing light. So the only thing that would create like a shadow effect was the fact that the light had to travel further to get somewhere. That's the only thing you would see. And so everything that is in shadow right now would be a lot less in shadow because the light would still always find its way there. It would just be a question of it taking longer, so the inverse square law would be more in effect, right? But that's it. Normally, shadows don't come only from inverse square law. Normally, shadows come because every time light bounces, it gets significantly weaker on the bounce. So you're not just seeing the inverse square law. What you're actually seeing is inverse square law plus the absorption. So every time the light hits the surface, you lose 30% of your light or something, right? And that's not at all what would happen if the light kept bouncing. Okay, so that's it. So in order to prevent our scenes from being artificially bright, I'm going to actually start making them absorb a little bit when you hit a surface, but that's all. Then for the MP text, what I want to do is, if we're coding this as NX, NZ depth, what I want to do is have everything point upwards, and I want the depth, let's say for the moment, to be 0, because we don't really need to care about that right yet. But I would like the light source to be higher than the surface, so that it shines down on it. So what I'll do is I'll bump it up for the light source. So what I'm going to do is create a synthetic value that's like if light, right, else not. So we're going to have this buffer be surfaces everywhere and light in one place. So what I want to do is have a way of saying what the light source, where the light source is. And one of the things that we specified is we specify a light P, which is the location of the light. So what I want to do here is, these are V3s. I don't know why I'm using Vec3. I'm in OpenGL parlance all of a sudden for no reason. So these V3s are specifying what we're going to write to the surface. What I want to do is change them if we're in light. So I actually don't need the else clause, I suppose, because I set them to the default values already. But if we're in the light, I'm going to set the front emit and the back emit to do different colors. I'm going to have a red light coming out one side and a green light coming out the other. Why? Just because that way we can see the difference between front and back side emission. I'm going to set the MP tech. So this is the depth again. That depth is going to be kind of closer to us. So maybe what I'll do here is I'll set this one to 1, and I'll set this one to 0, or maybe even more. I'll set this to like 10, and this to 0. So we've kind of got a lot of distance specified in there. And then what I'm going to do is say the direction of the light source is also going to be different. So the direction of this light source, let's say, is pointing 1. So it's shining a red light out the right side and a green light out the left side of it. That's just what it's doing, right? That's, who knows? I don't know why. That's just what it's doing. Okay, so that's our emission setup. Surface color for the light doesn't make any difference because it can't really bounce light around because it's an emitter. But so let's just say it doesn't bounce light. It only shines light out. Light doesn't bounce off it for now. Who knows why? All right. So taking all this into account, what we need now is some way of saying whether you're in the light source. What I want to do for that is take the distance to the light. So the distance to the light is going to be whatever location we're at right now minus the light location, right? So what we need to figure out is we need to figure out like this P minus light P, right? I should say delta to light. And then we've got a distance to light, which is just the length of the delta to light. At that point, it's a pretty easy thing to say whether we're in the light. We just have to have a light radius. How big is the light source, right? Let's say the light source is, a half a meter. That's pretty big. A quarter meter. Still pretty big. 1/10 of a meter, let's say. So it's a 1/10 of a meter, a decameter light source. So if the distance to the light source is less than the light radius, you are inside the light and we'll set it. Otherwise, we won't. And that's really all we need. We just need now to have some way of translating from the fragment P value to a actual 3D position in the world. So in order to do that, we need some information, but we've got glfrag chord, right? We've got the glfrag chord XY. We know that's going to range from 0 to 1080 or whatever. So we can just hack it. Again, this is a totally hacked lighting setup just for testing purposes. It doesn't have to be consistent, doesn't have to do anything smart. It can be completely dumb, and that's totally fine. So let's just assume that the Z value here, let's just assume that the distance from the light P in this case is not going to depend on Z. So we'll just set this P to be whatever the light's Z value actually is, so we know that that's not taken into account. And all we need to do is make the glfrag chord be something that roughly corresponds to what we want. So let's take that value in two parts here. Let's take the X and the Y. Let's go ahead and try to normalize that out. So if we expect to be running the glfrag chord from 0 to 1080, let's suppose we subtract half of 1080, right? So if this was our situation here, right? Something like this. And same over here. I guess technically this should be 1920. This is the x coordinate, not the y coordinate. So we've got those two being what they are. We then want to try and scale them a little bit. So that just kind of like, recenters them. And then we want to scale them a little bit. So I guess maybe what I could do instead, let's do it this way. Let's convert it to like a UV style. So let's divide it by the total. So now it ranges from 0 to 1. And then what I can do is just take -0.5 and add, in half the value to sort of scale me to a 0 to 1 range, right? Now 0 to 1 range is probably going to be too small, so we probably wanted to jack that range up a bit. So maybe we'll say like, you know, artificial range here, and we'll say that we are 10 in each direction, right? So there's our art range, negative art range to art range, negative art range to art range. Now this is going to be wrong. We're going to have a weird, it's going to be ovular because I'm not using I'm not correcting for these the same way. In fact, you know, I could do it. I could just do them both by 1080 and then it would be correct. Not correct, but it wouldn't be ovular. So maybe I'll do that. So let's go ahead and take care of any compiler errors we've got here in our shader. Redeclare built-in name frag data. So I guess that does have to be a vec4, right? That's what we're looking at here. nptext parser. So let's take a look. All right, so that requires semicolons. So it looks like it does want these to be v4s. That's fine. We can just write just to the XYZs of them. And that should be okay. And I guess technically if we really wanted to, we could say that these were RGB because that's really their color outputs. That's probably the more accurate way to state it. All right, so now we've got these that we're trying to write to. Already not great. Like I'm not seeing anything on the screen, which is not fantastic. So what that means is we're really never getting inside this distance to light here is never becoming a valid value, it seems. Where are we in time? We're almost out of time. So really all we have to do here is fix that calculation. Again, that probably has to do with the this-p. Again, that frag chord I feel like should be roughly correct, but then again, I don't really know. I feel like it should be ranging from 0 to 1080 in Y and 0 to 1920 in X, but maybe I'm wrong about that. The light P, again, should just be, you know, should be what it is. What I can do to double check that is I can set the light P temporarily to just be at 0. Oops. Or maybe I can't. Can't modify you. Okay. Let's use LP instead then. What happened? Redeclare built-in name GL frag data. So does that mean that it doesn't, that I just shouldn't declare this? That I should leave it undeclared? Because it's giving me a warning like it doesn't want that. Am I interpreting that correctly? Would it prefer that I just didn't put anything there? And let's see, I guess, if that's the case. So if I did that, let me see if the surface color and the nptec got written anything to them. Yeah, they did. So I guess it just wants me to not declare that at all. It's going to take care of it, and don't bother redeclaring it, I guess. So again, the only problem I'm having right now, as far as I can tell, is just I need to stabilize this GL frag chord better. Oh wait, you know what? We started at 12:15, so I actually have 15 minutes left. I'm not almost out of time. That's not true. So yeah, so all I have to do is just get this computation working more sensibly, and then we should be good to go. Because if this 0, 0, 0 here, what am I getting wrong about these coordinates here? So this P minus LP, take the length of the delta to light, the light radius, whatever the light radius is, then we say distance to light less than light radius. It should be set to these values here. So if we were to set these just to something regular, so if I just said this P equals GL frag chord, something like this, or if I just said something like that, and I set the light P to something like, let's say I set the light radius up to something like 10 pixels wide. I could just do all this in pixels and map the light forward, for example, and I should be able to see that work. The way that that would happen would just be to say, yeah, like this is a V2. That's set to the frag chord. The light position, in this case, is going to be, let's say, half of the value we expect, so 1080. 1920, 1080. So it's going to be the middle pixel-wise. The light radius is going to be 10 pixels. We should see a 10-pixel blob in the center of the screen, right? And we see it in the upper corner, which is pretty weird. So why are we seeing it half size? You saw that, right? You see what I'm saying? Up there in the corner. What's it doing? Why is it? We set it at half of the screen resolution. So unless we're drawing something twice as large as the screen for some reason, that shouldn't be happening, which, maybe we are. I'm not sure. But it seems like that's busted. Am I missing something? Frag chord XY, the light position is 1920, 1080, and we're having that, so that should be right in the middle of the screen. We're taking delta to light, and we're doing this P minus LP. I guess if the frag chords, so here's a question. Do the frag chords actually not have the delta offset added to them yet? I always forget what they're actually at. Okay, so it's 0, 0 is the bottom corner. So that's what I was expecting. So is this a half height texture for some reason? So if I was to take a quarter of that, would I show up in the center of the screen? I do. So what that suggests to me is that this texture is smaller than I think it is, and I don't know why. So let me just do a quick check to find out why, because I would like to know. So in here where we're creating our textures, you can see we've got a width and height in here that are set to the render width and the render height, and there we go when we start. So let's go ahead and jump in there when we're creating these so we can see what's going on. I'm going to switch out a hexadecimal view because we don't care about that. So the render width and never mind. I guess we're rendering at 960 by 540. Oh, right, probably because this card is too slow to render at full resolution. It's rendering at half resolution. Okay, don't care. Totally fine with me. Just wanted to make sure I knew what it was. All right, so that's all good. And so let's try to get, again, the rest of our stuff working where we can actually put the light position in here. So if I wanted to do that, what I could do is, again, take the LP, take the light position, which is now needs to sort of be recentered because the light position, again, is going to be sort of in meters, and now we want it to be in pixels. So what I can do is multiply it by this scalar here to sort of say, like, okay, let's multiply it out to the correct size in pixels here, but I don't really know what the scale factor should be exactly. It can be very approximate because, again, we're just using this for testing. I just need to be able to move it around, right? So you can see that that's all I need to be able to do is that. Now, it's not going to be centered properly as well, so what I would like to do is I'd still like to do that offset. So let's do the offset for the center of the screen. And let's make this a little more gradual. So, like so. Oops. So here, this way I can sort of move this light around slowly, which is all I really want to do, right? And so now what we should see is there's the light, again, that's kind of coming out of the light source. Here's our front side lighting, our back side lighting. Here's our surface reflectance, and here is our directional vectors, right? So we have everything that we wanted to have in place. Everything is now correct. And so what we need to build next is we need to build the downsampler, right? We need to build the thing that just takes and builds the progressively downsampled versions. Now we only have 10 minutes left. It's probably too little time to do that, but since this is just basic downsampling, we could get started on it anyway. It's not a huge deal. So let's just go ahead and do that. It's the one that goes the other direction. It's the back propagator where the most of the smarts are going to live. So let's take a look at the compute. What did we call this thing? Compute light transport. So this compute light transport here is going to be 2 phases. So first we've got the upward propagation. So this is like and this is the downward phase. So the harebrained scheme begins below this. We've got 2 phases, the upward phase and the downward phase. We're going to stick a to-do in here because we are not going to try and do the downward phase until next week. We will try to just sketch out briefly the upward phase, and you can sort of see what this is going to look like. So the upward phase is basically going to read from a larger texture map and write to a smaller texture map averaged values. And that's it. That's all it's going to do. So what we're going to try to do here as it goes down is we've got these light buffers and we know how many there are. So what we're going to do is we're going to go through and we're going to say we have a dest light buff index. That dest light buff index is going to range not from 0, which is the first one. That's filled in by the initial fill, by the initial lighting capture. So what we're going to do is we're going to take 1 is the first one we're going to write to, right? We're then going to write successively to each greater one as we go. That means that the source light buff index is always going to be the dest light buff index minus 1. So we're going to start on source 0, right to dest 1, source 1, right to dest 2, source 2, right? So it just kind of goes upward as it progresses. And so that's how that's going to work. And we are essentially going to do again, another full screen fill style thing where we each time fill the entire texture with a new set of samples. So if you look at what we're doing, probably the OpenGL screen fill back and forth, this is probably fine for our purposes, actually. This is exactly, I think, what we want to do. So I'll do OpenGL, begin scroll, OpenGL, end screen fill should do it, right? So let's go ahead and take this. So OpenGL begin screen fill and OpenGL end screen fill. In this case, we're going to take frame buffer handles here and write to them. This is going to be the dest buffer handle. So this is going to be the dest buff, and that's going to be a light buffer. We're going to writing everything, so it's going to be the write all buffer, and it's going to be as big as it was, and we're going to write to all the pixels, right? We're then going to do use program begin, use program end. It's going to be a new program, which is going to be the grid ups or multigrid light up. So we have a multigrid light up program. There's going to be a multigrid light down program that will do the opposite direction. That's going to be more complicated. And in this case, we do have to bind some textures. we're going to be reading from all 4 of these textures actually on the previous level. So it's going to be kind of a audacious nightmare scenario that looks something like this. It would be nice for us to probably stop doing this crap because you know, there already are in extended OpenGL ways of binding textures directly to a slot. Unfortunately, we aren't using. We aren't doing that. So let's just have a bind texture call here, which is like, you know, slot index. I guess we would need, yeah, you know what? I don't even want to deal with it right now. So anyway, we could have a call that's a single call that has all 3 of these in it. Let's just do it. Let's just do it. I'm just getting tired of it. So all this would be is just a GL enum slot, GL enum type, and then GL uint handle. So it's just like slot type handle. And then so, yeah, what I would say is we'd just be able to call OpenGL bind text. And in this case, we want to do the front text. So texture 1, 2, 3. None of these are multi-sample buffers, so actually we can just use GL texture 2D. And it's going to be front, back, surface color, mptech. Right, so it's going to look something like this. We bind each of the textures, and off we go. We then want something that's going to clear the textures because we have this sort of problem where the active texture handle kind of gets set wonkily. So at the end, we want to do something like GL active texture, you know, GL texture 0. Something like that. So that's it. That's the entirety of that sort of light binding nonsense. And really, that's most of what we need there. I need to go ahead and flush this out. We need the source and dest light buffers here. So OpenGL light buffer z plus source light buff index and OpenGL light buffers plus dest light buff index. So those are the 2 we have there. Dest buff should just be dest. And I think that's everything. So really, at this point, we need, we just need the program, and then we're done. I'm going to go a little over time because I'd like to just go ahead and get that program sketched in, and then that will set us up next week to be able to do the whole algorithm because we basically could just copy this routine here, change the textures around a little bit, and be ready to start fussing with our stuff, right? Okay, so this is going to be kind of like, not sure which one this is really going to be the most like. I guess it's going to probably be the most like this one, honestly. So compile final stretch. We're going to need some parameters here to help us out, but we can add those in. So let's make this be compile multi-light up. What did I call it? Multigrid light up. Oops. There we go. So yeah, read and write sRGB is not going to be on the table yet, I don't think, because we are just going to have everything in float for a while. Later on, we might have to work out whether we need sRGB encoding for some things to make it more efficient. Right now, I don't want that at all. In theory, there should be no parameters to this whatsoever, I don't think, unless we do want to pass U's and V's. Probably would make things easier if we did, because then we don't need to use the frag coordinates. See, the thing is, I think we're going to want to do our own sampling, and the fact that we're going to want to do our own sampling makes it a little bit harder. So we might just want to stay out of this business altogether. Let's see if we can. The thing that worries me is what we're going to do when we get down to having too few textures, too few texels to do 2 to 1. So that part concerns me, because if we start out at 1920 by 1080, eventually we get down to a certain resolution, there's nothing left to do 2 to 1 sampling on, and we would end up with artifacts there as the 2 to 1 resolution drop bleeds in. So at some level, we kind of want that UV to work. So you know, I guess I'll just do it. I'll just leave the UVs in there. We'll see how that does. We're probably going to have to be a little bit careful as we go. All right, so in this case, we've got sources and depths. So we've got source, emit text, front emit text. We've got back. We've got surface color. I guess we don't need tech on those. And then source NP. So these are coming in, and we need to do the same thing we were doing before, which is writing to GL frag color. So that means this is out of the question. I guess we do want tech on these because I'm going to sample them right away. So maybe we just say tech, and then we put in here that we're going to sample from them. So we just say, oops, I guess maybe I'll do it this way. So in here we'll say source front emit. And each of these is just, again, gonna downsample. In the future, we'll probably get more fancy with how we're doing these things. But for right now, we're going to start with the simplest possible thing. So that will sample from the textures. It will use the proper bilinear blend to do the sampling, which I think is probably roughly what we want. But again, we're going to have to play around with it, and we'll probably want to increase the quality of it. So we'll just let this do its thing, and then we'll write to our GL frag data the way that we were writing to it before. So what I'm going to do there is I'm literally just going to cut and paste this exact thing. And what we're going to do here is we're just going to literally assign the dest to the source. And that's all we're going to do for today. I don't know why we stuck tech on the end of this. Okay. So now we need to actually make these programs. And these programs are going to be a little bit more complicated in terms of what they actually look at than, say, our fake seed lighting program, which didn't really have to do anything. So we've got two of them. Multigrid light up program, that's the one we're going to do now. Multigrid light down program, that's the one we're not going to look at the moment. The multigrid light up program, it's really just textures. So it's going to be like this sort of thing. And so let's go ahead and take a look at these. Oops. So the multigrid light up program is going to need to specify all of these. It doesn't really need anything else. There's the frag UV that will come through, but I believe that's already handled in common. So it doesn't really need that at all. So I think all that we need to do is that, and then we should be able to just do our successive lighting from there. I'm pretty sure that's it. So let's go ahead and, after we do the multigrid compile, let's set those samplers. And so we basically want this code to happen a couple times here. And we want it for each of these saucy gentlemen. So yeah, each of these, source front emit text, source back emit text, source surface color, and source MP text. That should give us the full compile. Now we just need to actually bind it in there, and I'll put both of them in there for now. Multigrid light up program. Multigrid light down. So those are both in there now, and we need to actually call them. So when we have a settings change, they will get recompiled. And that will happen right here. And I think, let's see, use program begin, multigrid light up. Yep, that one needs to be fixed. And use program end is usually just does the common one, right? Okay. So compile multigrid light up. I'm going to go ahead and put compile multigrid light down in here as well. And let's see, we've got use program begin here where we're going to use the multigrid light up. We need to then actually have that do the binding that it should do. And in order to do that, let's see where that's at. It will not need any rendering setup. And it should just bind these in order. So it should just be source front, emit, source back, source surface, source MP. So all it really has to do is bind those samplers. That's all it does. And then it should be able to run the program. Now, we probably have some errors in there, but like I said, I'd rather just finish this up for now. That's not a very clear error message. To be completely honest with you, did you care to, did you want to tell me where you found the error by any chance? I guess in this case, maybe we need to get the info out of this thing first. So let's see. Okay, fine. So set the next statement. Can you give me some more info here? please. Vertex errors, fragment errors, program errors. Okay. So let's see. Vertex shader had no problems. Fragment shader had a bunch of problems. So let's take a look at those. Probably just typos, since we're not really doing anything in the shader yet. It's just a stand-in. Very, very simple. Okay. So first of all, these need to be v3'd. They probably also need to be RGB'd here because by default it'll sample a bogus alpha. So let's see, float to high 3K component. That may be it. Let's see what happens under validation here. Okay. So now we've got here we're looking at texture step that initial frame buffer 0. If I look at the next one up, I'm not seeing anything. So it doesn't look like we're properly sampling from these quite yet. And part of that also, we have to make sure that we're not using any MIP mapping on those, but otherwise, we might just want to leave this for next week. I'll do a quick check to make sure that there's nothing obviously broken, but that should basically be it. I also don't know why this is set to version 130. I think since we need version 150 on stuff, we should probably just change to version 150 everywhere, but we haven't done that yet. So, you know, we'll see. All right, so anyway, let's take a quick look and just make sure we know what's going on here. We're passing the fragment UV stuff in here, and we're sampling from that as we go. We're pulling those out. We're just writing out exactly what we sample into the output. That's about all that's going on. Again, nothing particularly fancy. So we want to make sure, I guess, that we're writing to the correct thing and reading from the correct thing. But that's about it. So here's the loop. We have the destination light buffer index as 1 and reading from the source light buffer index of 0. You can see us pulling out the source and dest here. So the source, we begin the screen fill to the destination. We're writing everything. So we begin writes to the destination. We do a use program begin on the Multigrid light up. We bind textures to 0, 1, 2, and 3 with the front emit, back emit, source color, and NP from the source, which is what we want. We then, we then don't draw anything. So we did have at least one obvious error, to say the least. But we still don't see anything on screen, so that was not our only error, right? But not drawing anything, obviously, is a problem. So there's that. So let's, again, just quick check, because, you know, just to kind of leave things in a reasonable spot. Let's make sure we're actually able to write. So what I want to do here is, again, set these values to something known. So what I'm going to do is I'm going to overwrite the front emitter with pure red. So what I should see is I should see the whole screen filled red when I go to switch to the next texture, and I don't. So what that means is it's not our texture sampling. We actually just aren't properly writing anything out right now. Because that front emitter should get written out to here, and at the moment, at least, it doesn't appear to be written out at all. So we've got a problem with just writing in general, not a problem with our actual shader. So let me see if I can track down what that actually is. We've got compile multigrid light up and multigrid light down, both being called. Presumably, we've actually got that compute light transport. Oops, compute light transport. So presumably we're actually okay here, and presumably we're targeting this write all frame buffer is the same thing that we're doing in our fake seed lighting. So in theory, anyway, in our fake seed lighting, because we were able to write to everything there, we should also be able to write to everything here, right? That's the, that is the only thing that would really make any sense, to say the least. So something bizarre is going on there, where for some reason we are unable to write to our source here, even though we're using substantively the same exact stuff. So I don't know what is wrong in this case. What I would like to try, and again this will be a little bit of an oddity, is what I would like to try here is what if I actually use the fake seed lighting on every level. I just want to see what happens there. It's going to be a little bit wrong. It'll move the thing up to the upper corner at the next step because the coordinates will be wrong, but that's okay, I think. So let's go ahead and see if we can do that. I'm just curious what happens. Here we go. Compute light transport. Oops. So there's a plus, and you can see that we're able to write to it. So there's just something wrong with our program that we're not understanding in this case, and I don't know what it is. So something's busted with the multigrid light up program, where it's not actually covering the pixels properly or something, right? We don't actually know what that something could be at the moment, but we know we're targeting the right frame buffer here. So we just don't know why we're getting into a situation where we can't write to the textures we're trying to write to using this program. Because like I said, I set, or at least I thought I set, in the fragment code here, I thought I set the front emitter value, so that should have overwritten frag data 0 with a clear red image. Let me go ahead in this case and try setting everything, and we can try to figure out why we're not seeing anything. Because that doesn't make a whole lot of sense to me. So that means we've got a stupid bug somewhere. Because that's like no pixels are getting filled whatsoever. Why aren't any pixels getting filled? What is the bug here? Oh, you know what? Probably because I deleted the input position, so it was outputting garbage. That's kind of a mistake. You know what I'm saying? Not great. Not really very good. Let's try that one more time. There we go. Now everyone's getting targeted properly. All right, a dumb typo. Nicely done. So now let's eliminate these, and hopefully now we're in a position where at least we're ready for next week to sort of work on that filtering. So there we go. Okay, so that's perfect. So you can see as we go up in resolution, we're doing exactly what we expect to do now, which is letting that lighting do what it wants to do, right? It's getting lower and lower res each time up. Same is true for each of these. Not sure why. It looks like we're getting red in both cases there. What's going on with that? Source back emit text, front back emit text, surface color, frag UV. Do we bind something wrong? Doesn't look like it. So let's just see what happens here. So here I am on texture 1, or texture 0. And you can see that that looks correct. Here I am on, let's say, texture 3. And that also looks correct. All right, here I am on texture 2. That looks correct. Here I am on texture 1, and that is wrong. It looks like we're writing out when we write to the back emitter, we're actually writing out the wrong thing. Now that could just be because we're sampling from it incorrectly, like source back emit somehow is getting something else in it. So let's just double check all those. So that's, I think, the only problem so far. Source front emit, source back emit, right? So these two look correct. Source front, source back, front equals front, back equals back. Frag data 0 is front, frag data 1 is back. So I see nothing weird there. And source front emit tech and source back emit techs, in both cases, both look okay as well. Right, that all looks pretty correct to me. So then when we do the bind, for multigrid light up, we do 0 is the front emit tech, and that presumably is how we said they should be right? 0, 1, 2, 3, 0, 1, 2, and 3. I don't see how we're getting that problem. Does anyone else see how we're getting it? That seems a little bit weird. Additional semicolon and GL get uniform local source back emit text in compile shader. Where's the additional semicolon? Ah! Thank you, stream. You guys have better eyes than I do. There we go. So that's all we need. Good, good, good. All right, so now we have basic upsampling. That's not upsampling, it's actually downsampling, but we have the basic up pyramid working. I guess that's about it. So I'll go to a brief Q&A now, though we're not really done with things. So any questions on what we're doing? We set ourselves up well for next weekend, I think, because now we've gotten sort of the drudge work out of that. And it should be relatively straightforward to now start experimenting. It's going to be a hard road to travel because presumably when I actually try to implement the lighting, it's going to be a huge kind of like thing like we did when we were trying to get the depth stuff working well, and we eventually came up with the depth peeling and it worked really well, but it takes some experimentation to get there. So if this lighting does work in the end, it's definitely going to take a bunch of experimentation to get there. It's probably not going to be the very first thing we try, but Frosty Ninja, is this going to be pulled out of the final ship to pull aside as DLC content to charge for? We need a Handmade Heroes season pass, and if you don't buy the season pass, you're not going to get the debug. You're not going to get the debug view, man. Like that's the debug view is like DLC. You gotta get the season pass for that. 4-bit lighting ideas for a good IDE integrated debugger for Linux There aren't any. You could try Qt Creator. It's got a lot of bugs, like a lot of bugs in the debugger, which is kind of funny. But it's the closest thing I've found because like it can at least see disassembly, I think, sort of, sometimes when it's in the mood. And it can usually sort of inspect things, and it usually can sort of save your breakpoints and stuff. It breaks all the time. And it crashes all the time when it's trying to debug and all other sorts of things like that. So it's not a good experience, but it's probably the best one that I've seen. And it lets you debug things you haven't built inside Qt Creator, which is important for people like me. Unlike there's a lot of IDEs, you can only debug something you build inside the IDE, which is useless if you use an editor that isn't the IDE. I guess not useless. You could still try to build. You could still set up a dummy build, I guess, or something. D7 Samurai, could you outline the idea for this lighting scheme? Basically, just take a look at yesterday's stream. That's what the whole thing was about. The idea is it's just going to be a multi-grid lighting scheme, which means we're going to propagate lights at a low resolution version of the scene and then push them down to higher resolution like lighting versions and keep going. It doesn't have a high probability of working. I've never heard of anyone do it. So I didn't have a better idea. Zillaresco, will I be able to pay money for an expansion that crashes every so often? Yeah, I think that's called an Intel integrated graphics part. All you have to do is buy. If you want your game to crash every so often, you just need an Intel driver. I think you're good to go. Is this a single player game or will there be some network multiplayer features? Single player game. Doesn't look like there's any more questions on here. All right, doesn't look like there's any questions. I'm gonna close it down. All right. Thank you, everyone, for joining me for another episode of Handmade Hero. It's a pleasure coding with you, as always. If you would like to follow along the series at home, you can always pre-order the game on handmadehero.org, and it, of course, comes with the source code, so you can program along with me and experiments with the source tree. If you want to ask questions, we also have a forum site you can go to. We got a Patreon page if you want to support the video series. We've got a schedule bot you can go to if you want to know when we're going to be live. And we got an episode guide that helps you catch up on old episodes. That's it for this weekend. We'll be back next weekend for another 4 hours of Handmade Hero coding, where we will try out the lighting, and we'll probably have something working next weekend. And by working, I mean not working, but we'll have something that does lighting, or at least computes lighting poorly. And so then we'll kind of have to take the next step and go, how do we make it really work and give us something we can actually ship? Which ought to be interesting, since this is a totally different algorithm than I've seen done before, so who knows? We'll see what happens. Until then, have fun programming this week, and I will see everyone on the internet. Take it easy, everybody.